Hello everyone, this is Dr. Sivan Singh, and once again I'm here with a new reagent. And of course, this is a common reagent which is used in the organic chemistry particularly. We can prepare epoxide, we can have ester, we can oxidize amines and thioethers in the presence of this perbenzoic acid. So that's why this reagent is a useful reagent, and today we are going to discuss the general features and the application part of perbenzoic acid. Okay. So if you see the general features of this per acid, then generally it is represented in the form of RCOOH. So this is the general formula of per acids. We have a variety of per acids which is available, and most commonly they are peracetic acid, perbenzoic acid, trifluoroacetic acid, and metachloroperbenzoic acid, which is also known as MCPBA in short. As far as the preparation of any of these per acid is concerned, then we can prepare any of these per acid once we are treating the corresponding acid with the hydrogen peroxide. So the preparation part is quite easy, but the useful part which we should be more concerned is that the application of these acids. So there are fundamentally four application of these per acids. The first one is epoxidation of alkene. So once we have alkene, we are treating with this acid, then we can have stereophysically, we can have cis or trans epoxide. So that is the first application. We can oxidize amine and we can also oxidize thioethers. So these are the other aspect of these perbenzoic acids. The last one is the oxidation of ketone, and we can have ester from ketone, and this is also known as Baeyer-Villiger oxidation reaction, and very, this is an useful reaction you can say in organic chemistry. We can prepare ester from ketone. So these are the fundamental applications of these per acids. Starting from the first one, which is called oxidation of alkene. So as we know that once we have this kind of alkene and we are treating with this metachloroperbenzoic acid in the presence of lithium, because generally what we are doing is that this MCPBA is crystalline solid, white crystalline solid, and once we are using this reagent, then we should use some halogenated solvent. So in the halogenated solvent, this is fairly soluble, so we can have a good combination, and then we are getting corresponding epoxide. So as far as the mechanism of this particular reaction is concerned, then we can easily understand from this PPT that we have an alkene, and once we are treating with this kind of per acid, then it generally follow concerted pathway. So what happens is that this alkene double bond will react with this oxygen. So you can see here this oxygen atom is getting attached with this pi bond, and simultaneously this hydrogen from OH is getting transferred to this carbonyl oxygen. So we'll have this carboxylic acid or acid functionality as a side product, and we have our epoxide as our major product. So the pathway which is followed for the epoxidation is concerted pathway that could be easily understood. So one more aspect of this particular reaction is that the reaction is stereospecific, and once we have this syn alkene, then we can have corresponding epoxide. We have trans alkene, then we have corresponding epoxide. So that is we have to remember. Another aspect of this epoxidation reaction, which we should, remember, is that whenever we have two pi bond, we have two different pi bond, then this reagent will do epoxidation reaction exclusively at electron rich subcenter. So like we have this two pi bond, we have this electron donating center, which is attached with this pi bond. So this pi bond will be electronically rich, so the attack of this pi bond on this oxygen will take place faster as compared to another pi bond which is there in the molecule. So the rate of oxidation of this pi bond will be higher as compared to other pi bond. So that's why oxidation takes place exclusively at one pi bond. So that you have to remember. This particular concept and the term which we have used earlier, that can be already seen from this example. We have these two pi bond, one is substituted pi bond and this is the terminal pi bond, terminal alkene. And once we are treating with this MCPBA in DCM, then we can see that the epoxidation exclusively takes place at more substituted alkene, and because this is electronically rich as compared to this terminal alkene, so that we have to also remember. So if we have cyclic system, cyclic alkene like norbornene system is here and we are treating with this per acid in the presence of chloroform, then the attack takes place from the less hindered side and we are getting almost 95% of this product, where attack takes place from less hindered side, because this is the exophase where it attacks. Interface is somewhat, we know that it is strictly crowded area, so attack of oxide takes place from this side, to a lesser extent. So we are getting a very minor amount of product in this direction. If we have a number of pi bonds, so like we have three pi bond here, 1 2 3, so we know that this each conjugated pi bond, and we know that the conjugated pi bond is somewhat stable as compared to isolated pi bond. So attack takes place exclusively at this alkene bond and we are getting epoxide. Another point we can understand is that this compound, which is called myrcene, beta myrcene, here if you see this double bond, then this double bond is tri-substituted. So the second point which we can also understand is that this pi bond will be electronically rich as compared to these two pi bonds. So epoxidation will definitely takes place at this carbon alkene bond. All right. Another point which we should remember is that whenever we have an allylic OH group in the ring or in the molecule, then this OH governs the rate of epoxidation or the position of epoxidation, because there is some electrostatic interaction between this MCPBA and this OH. So the epoxidation takes place in the direction where OH is already present. So this point we have to remember. It's a useful point that we should always remember. All right. So coming to the second application of this perbenzoic acid, we know that this can be used for the oxidation of amines. So if we have amine, tertiary amine, we are getting corresponding oxides. We have pyridine, so nitrogen is here, nitrogen has a lone pair, so it will oxidize and we are getting N oxides. We have amine, then this will be oxidized into corresponding nitro compound. So these are the second useful application of perbenzoic acids. The third application is we can get oxidized thioether compound. Once we are having this thioether, then it can be converted into sulfoxide or sulfones in the presence of this MCPBA reagent. So that is also useful. The last application of this perbenzoic acid is we can get ester from ketone using this perbenzoic acid, and this particular reaction is called Baeyer-Villiger Oxidation reaction. This is very useful reaction in organic chemistry. We all know this reaction. So what happens is that once we have a keto compound and we are treating with per acid, so it is per acid, it must be 3, then we are having ester. And how we are getting this, what is the possible mechanism, and if you want to know the mechanism, then we can easily understand that if it is a keto compound and oxygen has definitely a lone pair, once we are treating this kind of keto compound with per acid, then they will protonate first. So this will be protonated. Now it will be, O minus will be here. So now we know that once it is protonated, then the electrophilicity of this carbon will be increased. So electrophilicity of this carbonyl carbon will be increased. So oxygen can easily attack on this carbon. So we'll have this kind of tetrahedral intermediate. And once we have this tetrahedral intermediate, then the oxygen, since it has a lone pair, it will here, and one group will migrate to this oxygen and this ring will be open. So we have this carboxylate ion and then we have this kind of protonated ester, and since O minus is there, then it will take this hydrogen and we can have this ester, corresponding ester compound. And useful thing which we have to also understand is that the keto compound having which is substituted with the oxygen 18 isotope is used. So the ester has this in the form of carbonyl molecule, means oxygen which is there in the ester. This oxygen is basically coming from this reagent. This oxygen is not this carbonyl oxygen. So that's what we have to remember. The path which is followed here in the case of Baeyer-Villiger oxidation is the concerted pathway. So that is it. One more aspect of this Baeyer-Villiger oxidation is the migratory aptitude, because earlier we have seen that here we have two alkyl group, and we have shown that one R group is getting migrated. So if you see that you have two R groups, so either that R or this R can migrate. So which R group, which alkyl group will migrate? So this is decided by something which is called migratory aptitude in organic chemistry, and it has been found that if we have tertiary alkyl, secondary, primary and methyl group, then the rate of migration of tertiary will be higher as compared to secondary and then primary and then methyl. So this is the order which is followed. If we are talking about the phenyl ring, and then if we have some electron donating substituent there which is attached with the phenyl ring, then the rate of migration of that group will be higher as compared to phenyl. Electron withdrawing has lesser migratory aptitude, and this fact can be checked by this particular example. If you see here, we have two R group, nitro, and we have phenyl group. So once we are getting this tetrahedral intermediate, once we this paracid is getting attacked on this carbonyl group, so this R has higher migratory aptitude as compared to para-nitro. So this R is getting migrated. So this could be easily understood, and we have to remember this point. So there are several examples by which we can see the migratory aptitude and how ketone can be converted into ester once we are treating with these per acids. So you can see here we have cyclopentanone, and we are getting delta valerolactone, 6-membered lactone ring. Then we have this cyclohexyl kind of novinone system. We are treating with per acid, and then we are having this ester. As far as the migration is concerned, so this bond will migrate faster. The migratory aptitude of this bond is higher as compared to this one. So oxygen will be infringed between these carbon and this keto group. So you can see here. Similarly here, you can see here we have two migratory group. One is this one and second one is here. So we know that the rate of migration of this one will be higher. So it will migrate faster as compared to the CS2 group. We have this product. Similarly, we can get this kind of anhydride. So these are the four major applications of perbenzoic acid, and we know that using this perbenzoic acid we can do epoxidation. So this is the most useful. Stereospecific epoxides can be synthesized using this perbenzoic acid. We can oxidize amines and thioether. We can get ester from the ketone using this Baeyer-Villiger oxidation reaction. And of course, the mechanism is concerted, and there is some sort of migratory aptitude which is there in the functionality which is attached with the carbonyl group. So that we have to remember. All right, so I hope this lesson will be, it will help you to learn about the uh, application of this perbenzoic acid. So I hope definitely it will be helpful. Next we'll talk about selenium dioxide and ranitidine. Thank you.